So as everyone comes streaming back in, I'm going to start this afternoon's session. So that was a fantastic morning of important discussions. And now we transition into more purely science-focused talks with a series of 8 talks. Some of them videos, some of them in person. So Matt asked me to remind you that if you want to evaluate student posters and talks, you need to use this QR code. And we've got 4 students: Ruth, Moorman, Fiona, Clerc, Shuntaro, Hyogo, and Matthew, Kratochvil in this session. So keep an eye out for those and use that QR code to evaluate them. So first up is Molly Patterson. We've got a recording of her talk here. We're going to talk about sensitivity of the West Antarctic ice sheet to changes in temperature.
So thank you for inviting me to give this talk today about the WAIS 2C project. Before I start, I just want to take a minute and acknowledge that this has been a really large collaborative effort with many individuals contributing time and energy to developing this project. And I particularly want to just acknowledge some of our New Zealand colleagues who have played a really heavy hand in organizing this project and developing some of the new technologies that will be used to recover some of these new geological records that I'm going to be talking about. I also want to highlight that Antarctica New Zealand has contributed to managing this project, as with some support from various individuals at GNS Sciences in New Zealand. I also want to just acknowledge, basically the whole science team, which includes individuals from 10 nations, because through numerous workshops, everyone has really contributed in some fashion to trying to secure funding for this project. So this is just a brief overview of how this talk is kind of organized. I'm just mostly going to focus on scientific motivations for this project and kind of briefly talk about some of the new drilling technology and some of the on-ice and off-ice activities that are going to exist. And I'll just end with kind of highlighting how some of the US scientists specifically fit into the kind of different science disciplines associated with this project, and maybe highlight some opportunities for early career researchers down the road. So these flags here at the bottom of this slide really highlight the 5 countries that have committed to funding this project, as well as funds that have been committed through ICDP. There are pending proposals by some of our international collaborators. So a major objective of this project is to recover records from interior West Antarctica that may provide insights into past ice sheet sensitivities during some of the most recent times when global mean temperatures were around 2 degrees Celsius, higher than pre-industrial values. So kind of targeting these Pleistocene and interglacial periods, as well as these kind of Neogene warm periods like the Pliocene. So the idea is new paleoenvironmental data from these warm periods, when integrated with some of the new modeling studies that are going to be carried out, as well as some of the modern process studies, we can say something better in terms of understanding climate dynamics, and particularly feedbacks through solid earth processes and driving ice sheet stability as it relates to things like sea level change, future sea level change. So this objective is really motivated right by some of the observational evidence by glaciologists and geologists that just a moderate rise in global mean temperatures similar to the last interglacial could have a really big effect on the extent of the West Antarctic ice sheet. Some of this observational evidence includes the recovery of some Lake Quaternary marine diatoms that were recovered along the Cyprus coast margin, indicating the existence of maybe paleo seaways during some of the most recent interglacial periods. But then also on the opposite side of the Ross Sea, you have various initiatives that extended back to the 1970s and kind of later evolved into the Angel project. And those records really highlighted these periods during the Pliocene where open marine conditions prevailed for quite a while. But these open marine conditions, after went through a period of there was following these open marine conditions, went through a period of kind of this cooling event around 3.3 million years. And since that big cooling event, kind of the behavior of the ice sheet changed. It became much more dynamic. So kind of fluctuating between these two kind of end member states, between open marine with a grounded ice sheet across the drill site. And also highlighting here, also in from this record, from this one Andrel record, that there is also the evidence for Pleistocene interglacials to be more kind of like these Pliocene interglacial periods where ice cover is much more reduced. But then that's followed by growth of the ice sheet and kind of this persistent advance across the drill site. So there's this past physical evidence from the geological records, but then there's these kind of model-based hypotheses that estimate various scenarios of waste retreat during the last interglacial, right? So these are just 4 different scenarios that equate to 4 different estimates in terms of contribution to sea level. And they all kind of vary based on how the ice is configured and how much ice is there. Making sense of some of these model type scenarios, particularly for the Pliocene, has become even more difficult to resolve due to some new or more recent far field records that have developed these kind of novel approaches in reconstructing sea level change. So I'm talking specifically here about this blue curve. So this is a relatively new sea level record that was recovered from New Zealand. And basically the point of showing this is the big changes in sea level associated with this record are much greater than the kind of glacial, interglacial changes in ice volume that are recorded in some of these kind of classic paleoceanographic records, but also what is simulated in some of these ice sheet modeling studies. So the key science drivers are there's really 5 key science drivers, and the first 4 are really broken up into different time periods. Excuse me. Whereas the 5th kind of science driver is really focused on basically looking at changes in microbiological communities living in the sediments. So the 2 sites that we are planning to drill at is this first site is kind of adjacent to the grounding line associated with the Cam ice stream. So this site KISS 3, it's planned to be drilled during the 22-23 field season, and then in the following year the Prairie Ice Rise site is planned to be drilled in 23-24. So this is just a cross-sectional view of our kind of like best estimate of the age range of the sediments that we are anticipating to recover from both Cam and Prairie. And just for comparison, this black line here is the Andrel record that I've kind of highlighted previously. So at Cam, the target is really for this interval here, which is labeled as unit K1, and the kind of best hypothesis for these sediments is that they might be quaternary age sediments. So we might be capturing some cycles of, thick diamictites and maybe some thin diatomaceous mudstones. Whereas at Prairie Ice Rise, where the primary focus is the material below what we think is this Holocene grounding zone wedge material. But this Holocene material has some important kind of, can address some important science questions. But below this, what's labeled here is this horizon H. We are anticipating, and our best kind of hypothesis here is that this material is older than the material at CAM, the CAM site, and that it's probably Upper Neogene in age, so Miocene, late Miocene, Pliocene in age. And those age estimates are really based on reworked diatoms from some of the hot water, from some of the material that came up from during the hot water drilling back in the 1980s at around this site. So this Holocene age material can maybe fill some gap about the history along this margin between this time interval of what has been hypothesized as this early to mid Holocene retreat of the grounding line in this region, with grounding at Prairie Ice Rise around 1100 years ago. And there's going to be a really big effort to try to take some in situ temperature measurements of the ice and the sediment at this site to try to address some of these questions on ice sheet and solid earth feedbacks throughout the Holocene. So any quaternary material, interglacial material that we recover will be a massive bonus, because it will allow us to, whether it's marine isotope stage 5 or 11 or 31 or what have you, it really might allow us to start testing some of these different modeling scenarios. For example, in this scenario, we would kind of hypothesize a facies succession that looks something like this, where the interglacials are capped with these diatomaceous muds, and the detrital material might have a West Antarctic provenance signature, versus these types of scenarios where open marine conditions are kind of on the other side of West Antarctica. The interglacials might be capped by these laminated muds or massive muds with more of a detrital signal coming from East Antarctica. So the Pliocene, recovering any Pliocene material will be super beneficial and exciting to the project, right? Because we can tie it into some of the andril sequences on the other side of the Ross Sea, but also some of these offshore records that were recovered during IODP Expedition 374. So the recovery of Pliocene material will really allow for this really nice land to sea transect record across this margin, where the andril record is really kind of implied that prior to about that 3.3 million year cooling event, you had persistent kind of open marine conditions, with reduced ice extent across parts of, West Antarctica. But after that cooling event, you really fluctuated between these kind of two extreme end members over cooling and warming periods during the Pliocene. We don't anticipate to really recover anything much older than the Miocene, but there's always the potential for recovering reworked material, and that reworked material in itself has a really nice utility to try to maybe address some of these questions about the role of tectonics and carbon cycling feedbacks that are associated with the big climate events during the Miocene, like the middle Miocene climatic optimum and the cooling into the Miocene climatic transition. And what does the presence of a marine ice sheet mean for this climate, for this scenario? So while we anticipate these records to really be snapshot records, we're excited about the opportunity to kind of place them in some of the kind of the regional context of all these previous ocean drilling expedition records, but also these land ice drilling expeditions that have also taken place. So I mentioned this earlier, but there is a microbiological component to this project, and it really builds off the success of some of these previous projects in the region, right? So you can start seeing maybe something about spatial differences, but also given the age resolution of the sediments we aim to recover, we might be able to say something about temporal changes in microbiological communities during some of these past changes in environments. So these records are going to be recovered using a new drilling system that was developed by our New Zealand colleagues, referred to as the AID system. It's been inspired by the US ASIC system. And one of the advantages of the system is that it can drill through about 1,000 meters of ice and water and recover about 200 meters of sediment core. And it's much more lightweight than these other systems that were previously used. So the on-ice footprint is aimed to be very small with really minimal science to be done. And again, Antarctica New Zealand is going to provide the operational support for both these efforts with contributions, but notably with some contributions from USAP. The majority of science is going to happen off ice at an off-ice science workshop at the Orca facility at the University of Otago in New Zealand in months following the field seasons. The long-term storage of the cores is going to be housed at the Oregon State Core Repository, so the scientific community will have access to them. And then this is kind of the last slide. I'm just kind of highlighting here some of the different disciplines the USPIs kind of fall within this project. And we've been successful in securing funds for graduate students and even postdoc opportunities, as well as this potential for an Antarctic School 3.0 that we hope to have hold at Oregon State. So thank you for listening to this, and I hope you all enjoy the workshop.
Yeah, well, what I should have said at the beginning is that we're going to do, like similar to the previous sessions, we're going to have a discussion at the end, and most of the presenters who are presenting videos will be here to join in that discussion. But next we have Ruth Moorman. We'll get going with that now.
Hi, WAIS Workshop. My name is Ruth, and I'm currently a graduate student studying ocean dynamics at Caltech. But today I will be presenting some older work that I completed during my undergraduate in Australia with Adele Morrison and Andy Hogg. In this work, we were interested in understanding how anticipated increases in WAIS meltwater might affect near Antarctic ocean temperatures with an eye towards potential ocean-driven feedbacks to ice shelf melt. An existing body of work has attempted to address the question of how Antarctic waters respond to freshening using GCM perturbation experiments, where the freshwater flux from Antarctica is artificially increased. I've got a couple of examples of these up here. Generally, these studies have used coupled climate models with a relatively low resolution ocean component of at least 1 degree. And a fairly consistent result of these studies is that freshening of near Antarctic waters acts to stratify the water column and trap heat in the subsurface, leading to ocean warming. This warming has generally been seen close to the Antarctic coast and has therefore been interpreted as being related to a positive feedback on future ice shelf melt. An issue with interpreting the results of these modeling studies in this way is that low-resolution ocean models don't capture the small-scale dynamics on the continental shelf and at the continental shelf margin that largely dictate the water mass characteristics of Antarctic shelf waters and therefore dictate the ocean conditions experienced by the actual ice shelves. These unresolved shelf margin processes include the Antarctic slope front, which maintains strong lateral gradients in both salinity and temperature between on and off the shelf. It includes the formation and export of dense shelf waters across the shelf break. It includes polynya convection and the action of eddies to transport heat across the shelf break. So to really demonstrate the importance of these continental shelf margin dynamics, I'm just showing a map of temperature at 500 meters depth around Antarctica from a high resolution simulation. And you can see that there are some really notable contrasts between water mass properties on and just off the shelf, here shown in temperature. This visual should hopefully suggest to you that the response of the open Southern Ocean to perturbations is not necessarily going to be the same as the response felt by the Antarctic ice sheet, since the ice sheet is effectively insulated from the open ocean by a region with distinct dynamics that are not necessarily resolved in GCMs. Given this, we wanted to test those previous warming feedback findings using a higher resolution ocean model that better represents the dynamics that I've displayed here. I'm not going to go into a lot of experiment detail here, but suffice to say that we conducted 2 short meltwater experiments, perturbation experiments, with an ocean sea ice model that has a significantly higher horizontal resolution than previously used. And as a result, has a greatly improved representation of shelf break dynamics and shelf dynamics. The perturbation experiments we ran involved increasing the meltwater coming off these ice shelves highlighted in red, amounting to a 1.5 times and a 2.8 times stepwise increase in the flux of fresh water to the seas around the WAIS. These were then held for 10 years, and we looked at the response of ocean circulation to those perturbations. I should stress that there's no ice shelf coupling in this model, so the meltwater increases are externally prescribed. Now to the results. I'm going to start by looking at the mean thermal response of the continental shelf as a whole. So under control conditions, ocean heat is advected across the continental shelf margin and then lost to the atmosphere via surface cooling. The response that we would anticipate based on previous studies would be that as the region freshens, the surface cooling term decreases due to an increase in stratification. And indeed, we do see that in this model. The element that is not captured by coarser models is that the advective heating of the shelf declines in parallel to this reduction in surface cooling. The net effect is that the volume average temperature of the shelf waters here in the solid lines increases slightly at the start of both experiments and then decreases over the rest of the experiment as we see a shift from the surface cooling changes dominating to the advective flux changes dominating. By the end of both experiments, we have a slight net cooling, which is the opposite response to what we saw in those lower resolution simulations. By contrast, waters just off the shelf, so on the Antarctic continental slope, consistently warm over the simulations as shown in these dashed lines. As soon as we move away from this spatially average picture, our results get a lot more complex. We can see that there's a lot of spatial variability, both as to the sign and magnitude of the thermal response on the shelf. There are regions of strong heating, regions of strong cooling, and some differences between the 2 experiments as well. In our attempts to tease out these results, we came away with 3 broad mechanisms that combine to determine the sign and strength of the thermal response in different regions. I'll go over these now. The first is what we expected, so an increase in stratification traps heat in the subsurface and drives warming. And we particularly see this having an effect in regions where dense shelf water related convection declines in response to freshening. The second feature is a decline in the heat transport from the open ocean to the continental shelf across the shelf margin. Essentially, what's happening here is that shelf freshening increases the lateral density gradients associated with the Antarctic slope front. And this strengthening front impedes the transport of warm open ocean waters to the shelf. The balance between these 2 processes, the increased isolation of the shelf and also the increased stratification of the shelf, combine to effectively explain the net heat budget of the continental shelf region that started with that initial warming and then led to that cooling. However, in order to understand some of the spatial complexity and the regional responses, we need to think about one more mechanism, which is that as these fronts I've mentioned strengthen, the westward flow associated with currents in geostrophic balance with those fronts accelerates, as shown here. We have a slope front system accelerating at the edge of the continental shelf, and we also see some acceleration of currents poleward of the shelf break. These accelerating coastal flows act to homogenize shelf water mass properties, so cooling regions that are initially warm and warming regions that are initially cool. The most striking example of this is seen in the West Antarctic Peninsula region, where the direction of the mean transport around the peninsula changes changes direction. The mean transport, sorry. Essentially, as Weddell Sea shelf waters become increasingly buoyant, they no longer flow into the West Antarctic shelf. They no longer flow into the open deep ocean, and they are diverted into flow into the West Antarctic shelf where they drive cooling. So essentially waters that used to go through this pathway are now going around this pathway. So in summary, we found that freshening of Antarctic shelf waters by waste meltwater in a high resolution ocean sea ice model prompted thermal responses that were both spatially and temporally variable in sign and magnitude, and that they could be understood as the combination between these three different mechanisms. The big takeaway that I want to impress on the WAIS community is that the jury is definitely still out on whether or not there are positive ocean feedbacks to waste melt. The simulations presented here definitely have their limitations, but the study demonstrates that moving towards a more realistic representation of near Antarctic ocean processes can qualitatively alter the response of the region to meltwater, changing both the sign and the magnitude of feedbacks to ice shelf melt. Another big takeaway is that the sign of these thermal responses can vary between different regions around Antarctica. And I'll leave it there. Thank you.
Fantastic. Thanks, Ruth. A reminder, all the speakers are on Zoom, so thank you for that, Ruth. Next up, we've got Fiona Clerc. She's going to be telling us about how changes to the West Antarctic ice sheet could affect magmatic CO2. And she is in person. Thanks, Fiona. Take it away.
Great. Yeah, sounds good. Thanks. Okay. Hi, everyone. So today I'll be talking about mantle magmatism beneath WAIS, and this is work with my co-authors and advisors, Mark and Brent. So as an ice sheet is retreating, it can reduce pressures in the mantle, which can increase melting if the mantle is already partially molten there. And then this can lead to increased volcanic activity, which can in turn impart heat to the base of the ice sheets and enhance their flow. In fact, it was hypothesized by Richard Alley and co-workers that the deglaciation of the Greenland ice sheet increased volcanic heat output to the base, and that this ice sheet evolved, and that this influenced the evolution of the ice sheet over millennial timescales. And finally, increased volcanic activity can release additional aerosols and CO2 into the atmosphere, providing another climate tectonic feedback. So regarding the enhanced mantle CO2 output, there's been some estimates that have been made by scaling eruptive records since the last glacial maximum. So that's the top panel on here, where the deglaciation interval is the tan bar. And this change in eruption rates it has been suggested that can increase atmospheric CO2 levels by 40 ppm, which is the difference between these two lines on the bottom. However, the records may be potentially missing contributions from areas that are inaccessible, so like under ice, like West Antarctica. And understanding this process in West Antarctica is compelling, primarily because the West Antarctic mantle is volcanically active. The lithosphere is only 60 to 110 kilometers. There's a possibility for mantle plumes. There's a potential that the West Antarctic ice sheet collapsed rapidly in the past. The mantle may be carbon rich, and then radar measurements can link volcanic features with areas of enhanced basal melting, as shown in this figure. So this raises the question of what would be the influence of the collapse of WAIS on mantle melting in the mantle, and what those implications would be for magmatic CO2 and geothermal heat fluxes. Okay, the key uncertainty in answering this question lies in the geodynamic setup of this model. So in this talk, I'm just going to test one possible geodynamic scenario, similar to that from Verdau et al. And so this assumes that there's a mantle plume located somewhere near Mount Sidley in Murray Birdland. So that's and that location is inferred from seismic velocity anomalies shown in the bottom plot. And then for the thermal structure, I will just use geothermal constraints from the model from Papa and co-workers. And finally, I'll use an ice sheet history from the most recent version of the DeConto and Pollard and co-workers, in which the marine ice sheet instability initiates widespread collapse throughout WAIS. And I'll do the two different scenarios, which are the last interglacial on the top, and then a even more drastic Pliocene deglaciation. And since the models are in 2D, I've drawn a transect, and that's indicated by the red line on this plot. Okay, so the models are, again, two-dimensional. I'm using a mantle convection code. The rheology is viscoelastic and temperature dependent. So on the top plot of the temperatures, you can see there's a warm, low viscosity asthenosphere overlain by a rigid, cold lithosphere. And there's a thermal anomaly that's located at location 0, and that is thermally buoyant. And then the ice history is applied as a boundary condition on the surface, and that's represented by this green field, which is vertically exaggerated on this plot. And then the bottom just shows the degree to which the mantle is partially molten, so you can see that the melting is occurring near the plume head. Okay, so now I'll show some different snapshots from the model. So here's a background time step, where on the left we have the rate of pressure change. So under the dark teal colors are large rates of decompression that encourage mantle melting. And then the red arrows show the lithospheric flow. So here it's essentially stagnant. And then on the right, I'm showing the rate of melt fraction change. So in the orange zones, melt is actively being generated. Now I'm showing a model time step in which the ice sheet is thinning. So this is midway through the deglaciation. And you can see that the red arrows show that the lithosphere is rebounding locally, inducing large rates of decompression below, and that this influences the melt fraction field by leading to enhanced melting towards the interior. Yeah, so the left of the model domain is like the coast, and then the interior is to the right. So I'll just do one more slide, or the same slide, which shows the more drastic deglaciation history. And in this case, the mantle rebounds to a greater extent, and decompression rates are even larger, leading to even larger rates of melt fraction enhancement in deeper orange. So now I'll take these rates of melt generation and spatially integrate them to look at how the rate of melt production is changing volumetrically through time. So here we go. So the top panel shows the ice volume of that boundary condition forcing for the two different scenarios, where dashed is the last interglacial and solid is the Pliocene. And then the deglaciation interval is in the shaded 5,000-year interval. In the middle is the rate of melt production. So the orange line is the background, and then the black lines show that for both scenarios, the mantle, the degree of melting is being enhanced 4 to 13-fold relative to the background. And then that area under the curve predicts 800 to 300, 500 kilometers cubic of extra melt. Then we can also calculate the magmatic CO2 that could be exhaled to the surface. That's 12 to 60 gigatons, so that's slightly smaller than, that's somewhat small compared to the thousands predicted to be released during the LGM. But most strikingly, if all this melt were to be erupted to the surface, you would predict that would be enough heat to melt 13 to 60,000 kilometers cubed of ice or to raise geothermal heat fluxes by several watts per meter squared. So clearly it's not all going to be all erupted to the surface, but even some fraction of this could be having some influence on ice flow and be initiating dynamic feedbacks. Okay. So in conclusion, we've really just tested one scenario, but it's more of like a proof of concept that this is a process that could be occurring in Antarctica and could have some profound implications for the stability of that ice sheet. Thank you.
Fantastic, thanks, Fiona. Okay, next up we have Ricarda Dziadek speaking to us about, just getting the video loaded up, sticking with geothermal heat.
Hello everyone, my name is Ricarda Dziadek, and today I would like to present some of the work my colleagues and me did on geothermal heat flow in Antarctica. And I would like to present the results of our study that was published last month and dealt with high geothermal heat flow beneath Thwaites and Pope glaciers, inferred from Curie depth analysis of a new aeromagnetic grid compilation. Co-authors on this study were Fausto Ferraccioli from British Antarctic Survey and now OGS in Trieste, and also Carsten Gohl from the Alfred Wegener Institute. Now, for those of you who are not quite familiar with Curie depth analysis, I a little reminder. So in the back in gray, you can see Pippa Whitehouse's beautiful figure on solid Earth ice sheet interactions. And in orange, I try to draw some of the methods that we use in Antarctica to determine geothermal heat flow. As some of you know, we have to become a little bit creative because unfortunately we cannot just go everywhere, drill into the bedrock and then take a temperature to estimate geothermal heat flow, but we have to use a variety of methods. For example, looking at heat producing elements or radar echograms, and in the offshore areas we can use temperature probes to measure the sediment temperatures. A common method nowadays is the Curie depth temperature and looking at the Curie point depth. This depth, as you can see in this undulating line, marks a transition zone rather than an exact depth, and the temperature is roughly or approximated 550 degrees. From aeromagnetic data, we can estimate this depth, which gives us a temperature and a depth, and hence we can estimate a geothermal gradient and the geothermal heat flow. These methods we summarized in a review paper that was published last year, and here you can see figure 5 from that paper, where Alex Burton-Johnson was lead author, and Carlos Martin was also involved in this study. And I won't discuss the different continental-wide geothermal heat flow models you see above, but I would like to draw your attention to the lower two panels marked with the red square, because those two, in my opinion, depict the problem that we have quite well. So in panel F, on the left side, you see the mean of all 5 continental-wide heat flow studies that show the same trend. So East Antarctica is colder than West Antarctica. But figure G shows the standard deviation, and you can see that the errors are highest for the Antarctic Peninsula and basically beneath the West Antarctic ice sheet, which is a main problem because standard deviations of 50 milliwatts or more is quite high in the geothermal heat flow world. Some of this work has been part of a sub-action group that was formed in 2017 as part of the SCAR-CERSI program, which is now being translated into the INSTANT program, and people will continue to focus on geothermal heat flow in Antarctica, just to show you some of the names of people who are involved in this. And now our study that was published last month, which deals with aeromagnetic data. On the right panel, you can see the flight lines of different campaigns that we added to the AdMap 2.0 compilation, which was only available for the last geothermal heat flow studies, for example, by Yasmina Matos et al. Now, as you can see, we added a significant amount of new data, clearly processed everything, and made a considerable effort to really level all the lines, and then used this very local new compilation to estimate the Curie point depth. But first, I'm going to show you the new magnetic grids that we now have in this area, which will hopefully puzzle many PhD students to come, because there's a lot of information in the magnetic data. So very briefly, how do you get from magnetic data to Curie point depth? We used spectral analysis. Just to show you really quickly, we estimate the slopes of the spectrum of the deepest magnetic layer, and then linearly calculate the depth of the magnetic source of the deepest magnetic layer. And these are only points, but I'm going to show you gridded data, as you can see on the right hand side now. That's the Curie depth distribution. And you can see the Curie depth is shallow beneath Thwaites Glacier. That means high temperatures at shallow depths, which again translates into elevated geothermal heat flow. And the red circles depict the locations of volcanoes from Van der Vries' study from 2017. And he gives a confidence interval, so we are only showing potential volcanic locations with a high confidence interval. And you can see that Curie depth distributions correlate very well with that. And also on comparison with Yasmina Matos' Curie depth distribution, the band of shallow Curie depths continues beneath Thwaites Glacier into the Amundsen Sea embayment. Now, Pine Island Rift, for example, is not strongly represented. It shows up somewhat to the east. This might be that the method does not capture the rift, as it might be too shallow. And the geothermal heat flow based on the Curie depth can be now seen on the left panel. Again, this is a direct translation from Curie depth into geothermal heat flow. That is why the maps look very similar. But we do find extremely elevated geothermal heat flow in that region. Now, just to summarize a few points. So from a geophysicist point of view, the region has an extremely thin crust in some parts. There is evidence for a hot mantle underneath. Cornelia Spiegel in 2016 discussed a reactivation along older tectonic faults. We have a strongly heterogenic crust, and this region experiences some of the highest GIA globally, and we now find elevated to high geothermal heat flow. And these are all indicative for us that the temperature variations of the crust are quite strong. And we hope that this new grid will form a base for a new discussion on geothermal heat flow in that sector of West Antarctica. Now, for us, it would be highly interesting, of course, to have borehole temperature measurements for ground truthing of our data, and for future studies to look at heat-producing elements, for example, in the crust, and enhance the models that we have on that one. So with that one, I would like to close, and thank you for your attention, and I'm happy to answer questions now.
Fantastic, thank you. Okay, next up we have Shuntaro, Hyogo, and another video.
Hi, I'm Shuntaro Hyogo. Thank you for coming to my presentation. I'm a doctoral student with Hokkaido University in Japan. I'll talk about modeling ocean circulation in the Beringerhausen Sea. Let's start the presentation. This movie is horizontal distribution of potential temperature at 500-meter depth in Amundsen Sea and Beringerhausen Sea. It's created by Nakayama et al. 2018 model output. In this area, we can see clockwise Rossjaya and eastward ACC. Please attention to Beringerhausen Sea. Beringerhausen Sea have three troughs: Vega Trough, Latadi Trough, and Margaret Trough. And we can see CDW intrusions in these troughs. Although previous study focused on the ocean circulation in the Amundsen Sea, no analysis has been conducted for the Beringerhausen Sea using this ocean simulation that had consistency with observation data. Therefore, we conduct ocean simulation with a focus on the Beringerhausen Sea using the MIT GCM, and we evaluate model output to use observation data. We want to know general ocean circulation in the Beringerhausen Sea. Next, I'll talk about study policy and model configuration. First, we extend calculated time in the model. Old model's period is from 2001 to 2016, but new model's period is from 1992 to 2016. Second, we evaluated model output to use data. Third, to understand general circulation in the Beringerhausen Sea, we use time mean data. Besides that, we analyze seasonal variability of glacial meltwater and CDW intrusion. Fourth, discuss mechanism of seasonal variability, but today we don't have enough time, so I will only talk about number 1 and 2, 3. I'll explain about model configuration. This is model domain. We use MIT GCM. Horizontal spacing is about 3 km and there are 70 vertical levels. In addition, model parameters are similar to those of Nakayama et al. 2018. Next, we will show the result about model data conversion. This slide is vertical distribution of temperature and salinity about model and data. This section is located at this. Upper figures are observation data and down figures are model results. Left figures are potential temperature and right figures are salinity. First, this model will reproduce the intrusion of MCDW onto the continental shelf. Second, the model results agree with the water mass distribution in the surface and middle to lower layers indicated by the data. Next, I'll show pathway of the CDW intrusions in the Beringerhausen Sea. We conducted backward tracing particle experiment to use time mean velocity created by daily data. This experiment is conducted for water masses under the ice shelf with a water temperature larger than 1 degree. Gray patches indicate ice shelves in Beringerhausen Sea. Yellow dots indicate particles. Under this condition, most particles are under joystick ice shelves. Let's start the video. Please be careful. This video's time direction is opposite. In this experiment, the MCDW through Vega Trough, Rotary Trough, and Margaret Trough intrudes along the 500 meter to 600 meter isobars. On the model, inflow from Rotary Trough is not seen in the time mean field. So we focus on Vega Trough and Margaret Trough. We define red sections to calculate the time mean heat transport about Vega Trough and Margaret Trough. Vega Trough's heat transport is about 1.4 terawatt, and Margaret Trough is 0.5 terawatt. The similar experiments are conducted for years between 1992 and 2017, showing similar pathways. And it takes about 6 months from the Vega Trough shelf break to the southern Johann ice shelves. And it takes about 9 months for particle to get from the Margaret Trough shelf break to the northern Johann ice shelves. Next, I'll show spreading of glacial meltwater in the Beringerhausen Sea. We conduct forward tracing particle experiment to use time mean velocity created by daily data. This experiment is conducted for water masses under the Johann and stand ice shelves with a water temperature of the 0 degree or lower. The locations of particles are here. Please be careful, time direction is as usual. In this experiment, glacial meltwater travels westward. This is because Antarctic coastal current. For the particle discharge from each ice shelf to the Amundsen Sea, we calculated time from each ice shelf to the Amundsen Sea. This result is upper table. And after 2 years of model integration, about 21% of particles are located in the Amundsen Sea. In summary, we simulate the pathways of MCDW intrusions of glacial meltwater spreading. The MCDW through Vega Trough, Margaret Trough, and Rotary Trough intrudes along the 500 meter to 600 meter isobars, respectively. And glacial meltwater travels westward by Antarctic coastal current, consistent with previous studies. After 2 years of model integration, about 21% of particles are located in the Amundsen Sea. Thank you.
Great, thank you very much. Next up, we've got Alex Roble, sticking with that interface between the ice and the ocean.
All right, first off, I would like to thank the conveners of the WAIS Workshop this year for putting together a really excellent hybrid workshop that has allowed many of us to attend virtually, even though we can't be there in person. So my name is Alex Roble. I'm a professor at Georgia Tech, and today I'm going to talk about some work I did in collaboration with Earl Wilson, who's at Caltech, and Helene Sorossi, who's at Dartmouth. And the work is really focused on this question of what happens when at the interface between seawater, where it comes into contact with fresh subglacial discharge from underneath ice sheets. So what happens at this interface? And this is a problem that's been considered before by Ryan Walker and Roy Sayag in a pair of papers in 2013, where really they were focused on sort of the one-dimensional problem, horizontal problem, of how seawater can intrude underneath ice sheets against the hydropotential gradient due to the changing thickness of the ice sheet as it goes towards the terminus. And basically the conclusions that they draw, that both papers draw, is that only when you have tides pumping seawater or pressurizing seawater can you pump or bring in any seawater underneath the ice sheet. And so today I'm going to talk about sort of the added complication of what happens when we consider, which was not previously considered in these other studies, the compositional difference between seawater and freshwater. That is to say, seawater has salt in it, which makes it denser than the freshwater discharge from underneath ice sheets. And this creates the potential for layered seawater intrusions, where the seawater intrudes as what's called a salt wedge underneath the relatively lighter freshwater discharge above it. And the interesting thing about adding the sort of complication of composition, or of differing densities of seawater and freshwater, is that the hydropotential gradient turns out not to matter. And so I'm not going to go into detail about why that's the case, but basically it just has to do with the fact that when you have two layers that are vertically stacked on top of each other, the horizontal hydropotential gradient doesn't affect how far the denser layer intrudes underneath the lighter layer. And so this previously has been shown in work by Earl Wilson in a paper last year in the Journal of Fluid Mechanics, where he showed using both laboratory experiments and theory that in the specific case of laterally confined subglacial channels, so something like a Roethlisberger channel, you can have the potential for kilometers of intrusion of seawater within the subglacial channel under grounded ice. And so in this image here, you can see the freshwater in blue coming from the right-hand side of the screen, and underneath it is intruding relatively denser seawater in the clear liquid. And so today what I'm going to talk about is a generalized version of this theory that applies to a wider range of hard and soft-bedded subglacial hydrology. So this new theory actually encompasses Earl's theory that is specific for laterally confined channels, and allows us to draw some broader conclusions about the conditions under which we expect seawater intrusion to occur underneath ice sheets. And so the assumptions that go into this theory, which unfortunately I don't have time to go into complete detail, but if you're interested, I invite you to find the mathematical details in our preprint, which should be up on the cryosphere discussion soon. The assumptions that go into this theory are that water flow is subcritical, that is, the Froude number is less than 1, that entrainment between the salty and the fresh layers is negligible, which is appropriate for subcritical flows, and that ocean currents are relatively weak compared to the rate of discharge of fresh water from underneath the ice sheet. And so just jumping straight to the predictions of this theory, what we end up finding from the theory is that in any place where we have in any place where we have a hard bed, so that's to say an impermeable bed, where the bed is sufficiently reverse sloped, where the subglacial hydrology is thicker than centimeters, or where the discharge rate of fresh water is relatively low, that is, it's lower than sort of order centimeters per second, we expect to find intrusion distances of hundreds to thousands of meters upstream of the terminus to grounding line. Conversely, when we think about soft beds, what we find is we generally do not expect that there's going to be very much seawater intrusion occurring through these soft beds. And this is simply due to the fact that subglacial till is just not very permeable to water. So the theory generally predicts that we will only get a few meters of seawater intrusion, which is really not important for many of the purposes that we care about. So finally, I just want to talk about why is seawater intrusion potentially important. So we try to test the potential implications of seawater intrusion for the dynamic evolution of marine ice sheets by introducing a new parameterization into the ice sheet and sea level system model, or ISSM. And basically what we do is we allow for there to be ocean-induced basal melt upstream of the grounding line in ISSM over some distance, L, which is a prescribed parameter in the model, a new prescribed parameter in the model. And so the idea here is basically that in this parameterization, the melt rate goes from what it is underneath floating ice, which you can see here is the dashed line is the terminus or the grounding line in the model, and then it linearly falls off to 0 over the intrusion distance L. And what we end up finding in two benchmark transient simulations of marine ice sheet retreat, so one is an idealized configuration from the MISMIT plus ice sheet model benchmarks, and the other is a well-tested configuration of Thwaites glacier evolution over the next few centuries. In both cases, really what we find here is that even with just a few hundreds to thousands of meters of seawater intrusion induced melt upstream of the grounding line, you can get anywhere from 30% to 100% faster ice volume loss rates from marine ice sheets. So that is to say, you can get up to double the rate of marine ice sheet volume loss just by having a few kilometers of seawater intrusion upstream of the grounding line. And this is equivalent to approximately doubling or tripling the rate of melt underneath the floating ice. And this is really, we kind of focused in these simulations on these benchmark cases, but it's actually not surprising because if you look at previous intercomparison projects, what they show is that models that accidentally include intrusion by allowing for melt upstream of the grounding line and sort of the way that they numerically implement melt on floating elements, model elements. What they find is that models that sort of erroneously include a few kilometers worth of intrusion have the highest contributions to sea level rise in the entire intercomparison project. So here I'm just pointing out 4 models and their contribution to sea level rise from Antarctica, and these 4 models are the 4 models in the intercomparison project that accidentally include intrusion. So finally, just my final takeaways for you all from this work is that the predicted extent of seawater intrusion from this theory is still highly uncertain, right? So we talk about sort of hundreds, it can extend all the way up to hundreds of meters to sort of tens of kilometers of seawater intrusion, but it can also extend down to 0, in certain cases. So there's uncertainty over 4 orders of magnitude in the extent of seawater intrusion. Because the reason for this uncertainty is that the observations of subglacial hydrology near grounding lines is currently so sparse that it's really impossible to rule out the possibility that seawater intrusion is occurring and that it may extend up to tens of kilometers inland. And so the consequences, as we've shown for the modeled marine ice sheet sensitivity to climate change is potentially huge. I mean, up to a potential doubling of the amount of ice loss. And so that really tells us that this is a process that's worth studying with further observations, new models, and further laboratory experiments. So thank you very much, and I'm happy to take your questions during the panel.
Thank you, Alex. And then in person we have Matthew Kratochvil talking to us about talking to us about Binchadler ice stream. Take it away. Yeah. Just forwards back, please. Forwards back, rather give you a minute.
Okay. Hi, my name is Matthew Kratochvil. I'm a master's student at LSU, and along with my advisor, Dr. Philip Bart, I'm here to talk about the quantitative analysis of a maximum rate and minimum duration for a 200-kilometer stepwise retreat within Binchadler ice stream at around 11,500 years before present. So to begin with, as paleoglaciologists, we're mostly interested in the retreat history of ice sheets in order to better understand how they can affect the modern day calculations we make. For example, here we have a map by Halberstadt et al. In 2016 that shows the relative retreat history of the West Antarctic ice sheet within the Ross Sea, based off of primarily seafloor morphology. Now, we're primarily concerned with these large retreat events. Specifically, if you look at Joides, between 4 and 5, and Glomar Challenger between 3 and 4, and the subject of today's panel in the Wales Deep Basin between 2 and 3, which carries the Binchadler ice stream. So, Binchadler ice stream, in the past, this last glacial maximum had 3 major still stands. First, on the continental shelf at the last glacial maximum, then in the middle continental shelf where it deposited 7 different grounding zone wedges, and then it finally had a 200-kilometer abrupt retreat back to Roosevelt Island around 11,500 years ago. And here is a bit of interpreted seismic from Bart et al. 2018 showing the different grounding zone wedges. And the axis along the trough. And this leads us to 2 different questions that we want to answer today. Primarily, what was the maximum rate of grounding line retreat within this 200-kilometer area? And at that maximum grounding line retreat, how long would the Binchadler ice stream take for it to go from grounding zone wedge 7 all the way back to Roosevelt Island? So, in 2015, Nathaniel B. Palmer conducted an extensive geophysical and geotechnical acquisition campaign to study the grounding zone wedges within the Wales Deep Basin. The campaign subsequently uncovered a series of smaller grounding zone ridges along the top set of grounding zone wedge 7. Here you can see a 3D view of it looking from the southwest. They primarily have a morphology that's similar to Degier or transverse moraines. There's over 45 of these different ridges. They range in heights from 8 to 11 meters. They can be anywhere from 800 meters wide. They have a spacing of a kilometer, and they can be about 40 kilometers in length. We interpret these as the spatial record of a rapid collapse of the Binchadler ice stream along the top of grounding zone wedge 7. So, along with that beautiful multi-beam bathymetry, we also collected sub-bottom profiler data that shows these different ridges as chirp transects. So here's an example using the original data taken from the Palmer from A to A prime along the ridge field. We can clearly see we have a clear basal reflector, and using that along with the seafloor bathymetry, we can create isopachs of the volumes of the ridges across the geophysical survey. So this is a very simplified version of my methods, but essentially what we can do is we can take these 2D volumes and then divide by the streamwise flux of the Ben Shetler ice stream as published by Barton Tulzik in 2020. And the results is the time elapsed to deposit a set of ridges or a single ridge depending on your scale. Then we're able to take the 2D distances between the first and the last ridges, divide that by the time elapsed to create a grounding line retreat rate as a matter of meters of average retreat per year. So with that, I'm going to walk you through a really quick example. Here's some data that I collect. Here's our spatial data. We have two sets of sub-bottom data. Today we're going to be focused on the southeastern corner along top of the multi-beam. So with that, again, we're able to create our isopach. This is all in height, and we're specifically going to be looking at one profile 5 along that isopach field. So to begin with, we have to have our flux from Barton Tulzik, and then we're able to take that flux and divide it by the width of the Wales Deep Basin, which gets us our streamwise flux. In this case, it's 4,700 square meters per meter line of grounding line per year. And then we take our volume of the ridges, which are identified in the yellow boxes and numbered from 1 to 25. And by dividing the volume with the rate, we get a time elapsed, in this case 29.9 or close to 30 years. And with the distance between ridge 1 and ridge 25, we're able to calculate a grounding line retreat rate in this example of around 805 meters of retreat per year along this profile. So, since they're so spatially variable, we have 8 different profiles across the entire region, ranging from 200 meters a year of grounding line retreat to 1,300 meters of retreat per year. And in comparison with the fastest rates from the Amundsen Sea sector, we find that our rates tend to be slower than the published rates for the fastest instances of both Smith, Thwaites, and Pine Island Glacier. So, in conclusion, we were able to use the fluxes from the breakup of the Ben Shetler ice stream and volumes taken from the geophysical campaign to determine a maximum streamwise grounding line retreat rate for the collapsing Ben Shetler ice stream that ranges from 200 meters a year to 1,300 meters per year. If we were to take the maximum rate of 1,300 meters per year over across the entire 200-kilometer ice shelf collapse, it would take less than 2 centuries for it to completely go from Grind Zone Wedge 7 to Roosevelt Island. We're hoping that these streamwise rates can be useful for as boundary conditions for future ice shelf modeling. And with that, I'm done.
Thank you, Matthew. That was fantastic. It brought us back onto time and also gave us just a couple of extra minutes to sort out some technical with this adapter up here. Well, we're getting lots of good questions in for Alex and others on the chat. So if this takes a while to sort out, we can always go to those. But otherwise, we're going to have a good discussion at the end now that we're back on track time-wise. Okay, we're back on. And then for the final talk in this session, we've got Johann Klages. And I believe another video at the end. Great, thank you.
Yeah, good afternoon, everyone. My name is Johann Klages from the Alfred Wegener Institute, and I would like to thank you first for giving me the opportunity to present our latest research here today. Many people were involved in this study about a drill record that we recovered now about 4 years ago from the Amundsen Sea embayment shelf. in about 1,000 meter water depth. And I'd like to convince you that we found strong evidence for a West Antarctic archipelago that was covered by cool temperate forests during the early Oligocene glacial maximum. So mainly for this study, people and colleagues were involved from the British Antarctic Survey in Cambridge, the University of Southampton, the Northumbria University in Newcastle, the Marum Research Center in Bremen, the UK IUDP program, the GeoMar Research Center in Kiel, and from us, the Alfred Wegener Institute. As you see here in the upper left corner, we look into a time 34 million years ago, so the so-called Eocene-Oligocene boundary. And for this particular time last year, Paxman and colleagues, honor was already in 2019, published a new topography data set for this time. And I put the core location where we recovered the core into that data set, and you see it's right here where we have this outlet of water masses coming from the West Antarctic interior here, still connected with the Weddell Sea. For this particular time, it is still largely unknown which land masses were already covered by ice sheets, so during this early phase of the Kenozoic ice house. And now with this first West Antarctic shallow marine drill record that I'd like to present you, so that we recovered during this expedition PS104 in early 2017. That allows now first insights into the paleo environment in this part of the Antarctic continent that is considered as being the key region for understanding West Antarctic ice sheet evolution. And here on the seismic stratigraphy image, you see the context where we recovered the core. Was most likely some Eocene strata here, and then the Oligocene strata here, and we dipped into these Oligocene, so earliest Oligocene strata, about 10 meters into that. And how we did that, I'd like to show you in a short video that I have here. So we used the Mibo seafloor drill rig that we can send to the seafloor from our ship, the Polarstern, and basically it lands on the seafloor like a spaceship does, and sits there on the seafloor, in our case about 1,000 meter water depth, and can be remotely operated from the ship. And there are always about 3 to 4 technicians that are responsible for the drilling process itself. We have 20 HD cameras working in parallel down there at the seafloor so that we always know what's going on. And then the drill process starts. We have 2 magazines for this Mibo drill rig, one with empty outer and inner barrels, and then 1 magazine for the ones that will hopefully be full before they get up to the surface again. And then the drilling process starts. And with this Mibo drill rig, we can drill down to 80 meters sediment depth. As I said, for our core, it was only 10 meters, and that was mainly because of weather and sea ice conditions that became just too serious for letting the Mibo operate any further down on the seafloor. What did we get? So here you see some line scan imagery of the core down to 10 meters below the seafloor. And we see an extremely fine-grained lithology that virtually lacks any clastic sand grains. So we see absolutely no indication for ice-rafted material. But what we see is a constant delivery of the clay mineral illite, implying very intense physical weathering on nearby land. But we also see an absence of kyelenite, which at the same time implies glacial inactivity in the bird subglacial basin, which is the only known source so far for kaolinite in the region. And this bird subglacial basin is covered today, mostly covered by Thwaites Glacier. The paleomorph assemblage that we found is dominated by Notophagus pollen. Up to 90% of all pollen we found are Notophagus pollen throughout the record, thereby suggesting climate conditions very similar to those presently prevailing in Patagonian Notophagus forests. So in a cool, temperate climate with mean annual temperatures of 5 to 6 degrees Celsius, summer temperatures of around 8 to 9 degrees Celsius, and winter temperatures of 3 degrees Celsius. And in a precipitation regime of about of more than 600 millimeters per year. Not only we got these paleomorph-based temperature estimates, but also TEX 86 sea surface temperatures, which successively decrease towards the core top from 12.5 degrees Celsius towards the core base, and to 8.5 degrees Celsius towards the top. And that nicely corroborates the pollen-based temperature estimates. We see a very high terrestrial aquatic ratio, implying a high input of terrestrial organic matter to the site. And at the same time, the bit index of more than 0.5 suggests that most of this influx was facilitated by rivers and streams. Finally, some strontium isotope dating together with our paleomorph and bulboforma biostratigraphy, we could constrain an age of around 33.8 plus minus 600,000 years, so 33.8 million years. And because of that, the magnetic reversal that we see in core 3R, so right about here, that relates to the transition from Crone C13R to C13N at about 33.726 million years. So coincident with the base of the early Oligocene glacial maximum. So in summary, we are pretty confident that we have the first direct evidence of West Antarctic continental paleoenvironmental conditions during the onset of the Kenozoic icehouse. So that means the early Oligocene glacial maximum. We see a cool temperate climate without any indication for the presence of marine terminating ice, and probably even not in the West Antarctic hinterland. And if at all, only the minimum 34 million year Paxman topography reconstruction can be verified by our data. The multi-proxy results I just presented to you, combined with other circum-Antarctic paleoenvironmental data across the Eocene Oligocene boundary, will serve as target values for further development of the AVI Earth system model that we're working on right now. And that for the first time couples or fully couples the ocean, atmosphere and landmass components, including interactive vegetation. So we are working on this right now, but expect first results very soon, and then hope to present first results of all that I just presented to you very soon. Well, thank you very much for your attention. Bye.
Well, thank you so much, all 8 speakers there, and special thanks to the students and early career scientists, and a special thanks to the 2 students who were here to present in person. So what we've got now is 25 minutes of discussion on these topics, and it just shows you these talks how wide-ranging the topics we need to discuss are when it comes to marine ice sheet sensitivity, ranging from time scales, different processes, different spatial scales. So Fiona and Matthew, maybe I could ask you to come up and become part of this in-person panel, and the speakers on Zoom, I think almost all of you are there. I'm going to ask you to stand by for questions from Zoom and in person. So We do have some coming in from Zoom, and if you want, anyone want to stand up and use this microphone to ask questions in person of our speakers too. Oh, okay, so on Zoom we've got Rob asking a question. Rob, would you feel comfortable unmuting and asking your question? Or I can paraphrase. Okay, I think so. From what Rob gets from Johann's talk is that it suggests there's plenty of time for iron derived from mineral weathering to be involved, and he asks questions about this and wants to know, but is this precluded by the highly episodic nature of the flow? Johann, maybe you can address that.
Can you hear me?
Yes.
Okay. I don't really know if I have to read the question again. So we have to have
this is Rob. Sorry, I'm late to the party here, but I can rephrase the question if you like.
Yeah, that would be great, because you're talking about a subglacial system here, and so we are pretty confident that we didn't have one at that time, right at that location, but also in the hinterland. So yeah, it would be great to rephrasing it, because it seems to be a pretty chemical question here.
Yeah, it's a chemical question. I'm a trace metal biogeochemist, and I've done work, and I'm interested in sources of iron to West Antarctic shelf systems, and very little has been done or really thought much about in terms of the contribution of the subglacial system. I think mostly because people don't know what to think about fluxes and how important they might be relative to other sources of iron. But I've been thinking about that, and you know, I don't know much about the physics, and I'm not a glaciologist, and I don't know enough about the subglacial system, but if it were flowing at a particular location at a slow rate, and then every few years you had the drainage of a subglacial lake or something like that, and a sudden increase, it would make a difference to the iron geochemistry in the water column outside, whether seawater had already intruded and formed a salt wedge and allowed interaction between what would probably be low oxygen or anoxic meltwater and oxidized seawater derived from the shelf water column. It's a general.
Okay, all right.
I didn't mean it as a question. I actually meant it just as a continuation of the discussion that was occurring at the end of the session.
Yeah, because the only thing I can say to that, so that actually we don't see any indication for the presence of ice yet. So at that time and at that particular site, so it was all covered, and the site itself was bathed in seawater completely. So and no indication for any meltwater or even material that was transported by ice, either sea ice or icebergs.
Okay. Okay, thank you very much.
You're welcome.
Great, thank you. Maybe that's a good time, Alex Robel, whether you could unmute and maybe address some of the questions which have been coming into you about the saltwater intrusion you were talking about, and maybe specifically Rob's question as well, if it's relevant to the response we just had.
Sure, yeah. So I tried my best to address the questions in the chat as they came up.
Not hearing you, Alex.
You can't hear me?
Yeah, we can hear you, Alex. And I apologize to ask you to answer them again, but as the people in the room won't be getting the chat necessarily.
Oh, right, okay, yeah. So maybe if I can summarize, and apologies, wouldn't be a WAIS virtual workshop if my dog wasn't barking. that I think there were a few questions about basically like if you have a strongly stratified two-layer system, right? So you have fresh water on top and salty ocean water on the bottom that's getting underneath the ice sheet, right? How do you actually melt, do any basal melt? And this is the kind of situation that you see in places where you have double diffusive staircases, where you have relatively fresh water over salty water below. And so it is still possible to elevate melt rates in that situation. You can get heat flux occurring, through the staircase. It might not be at the same rates as on the floating ice. And so I think that there's definitely some work to be done to sort of understand that. More the point here was to kind of do a back of the envelope, in a sense, calculation to see if you did have elevated melt rates that were being caused by the intrusion, what sort of effect would they have on the ice sheet dynamics?
Thanks, Alex. So we've got a question for Fiona from Carson. Maybe I'll just read it out. If magmatism/volcanism was more active in times of a minimum ice sheet, wouldn't one expect to see lots of volcanic clasts in offshore drill records in most warm interglacials? So would you expect to see evidence in the sedimentary record of the processes that you're talking about? Maybe something.
I mean, I don't know much about the sedimentary record, and I think it probably depends on the magnitude of this effect, right? Yeah, I mean, that's an excellent question, and definitely something to look into. And I don't think that there is any evidence available that there's, or that anybody has looked in the sedimentary record for that specifically. So thanks for your question.
No. Okay, so I mean, this is a discussion topic for the room, of course, with the experts in sedimentary records here. If you know of this records to preclude or support evidence for this, is something to talk to Fiona about. Next up, maybe you can use this microphone. Ask your question. Thank you.
Hi, this is a question for Alex, if you can hear me. Thanks for the great talk. So, do you have a sense from any of your simulations, or maybe if you haven't, some expectations for the sensitivity of horizontal intrusion distance with respect to, elevation changes, both positive and negative?
So I can't thank whoever that is because I can't see the speaker, but thanks for the question. As far as I'm not quite sure what you mean by elevation changes, if you mean the elevation of the bed. And so, for example, basal slope, there is sort of an interesting prediction from the theory that at sufficiently reverse sloping beds, you should predict unbounded intrusion, right? This is actually a prediction that Earl made in his laterally confined theory, and then we extended it sort of for a broad range of beds. And so in places where you have reverse sloping beds, you sort of expect intrusion distance to be enhanced. And, if, everything else being equal, it can potentially extend quite far inland. Of course, the bed topography is bumpy, and so we don't necessarily expect it to sort of extend infinitely long and other things are happening at the same time. But bed slope is definitely an important factor.
Thanks, Alex. Yeah, another question from the room, please. Thank you.
Yeah, hi. I have a question for Alexander. I'm Lisa. I'm a postdoc at Rutgers. And I was just wondering, I was trying to picture this salt wedge idea, and I was wondering what you think the rate of recirculation in that system would be. In particular, I'm interested in if there were a biological community that's using up oxygen, would there be enough time for that water to go anoxic, or is it kind of recirculated very rapidly with tides and so on?
I mean, you can do a back of the envelope calculation, which we've kind of thought about a little bit to think about mixing, or to start to think about mixing. We're basically, you know, if we're thinking about intrusion over a length scale of hundreds of meters or kilometers, and you know, either freshwater discharge, or, I mean, in the theory, we assume that the ocean is stagnant, which is certainly a big assumption. But, you know, if you envision that ocean currents are providing some velocity at the grounding line, then you can kind of calculate like rough residence times for water within this salt wedge. You know, and for the kind of situations that we were thinking about, again, you know, where entrainment between the two layers is basically negligible or very low, you know, the sort of residence times are of the order of, you know, days, basically. So I don't know, you know, how that compares to the sorts of timescales that you're interested in, but you know, there definitely will be sort of renewal of the waters over time.
Yeah, okay, thank you.
Great, Brent, next to me. I think we're in person still, no one.
So Fiona, enjoyed your talk. So I'm thinking there's a fairly extensive record of terrestrial volcanism and dates of lava flows, as well as ashes preserved to a certain extent in ice. Not every ice thinning should induce an eruption, but have you looked for any correlations between known periods of ice mass volume change and eruptive activity in Antarctica?
I've like looked through some of the data. There's nothing that like jumped out at me. So,
thanks.
It's kind of, I guess the record is like somewhat sparse in that it wasn't clear. You know, I think ideally you would have like really precisely dated records, and then like have, you know, look for textures in terms of whether like an ice sheet was present during a given eruption, and then try to make inferences from that. And I think, you know, also the challenge is that like a lot of it is subglacial, so you're really limited to what's on the exposed at the surface.
I guess as a follow-up, if you put on double fuzzy goggles on the timing of ice mass volume change and eruptive ages, is there any correlation with ultra fuzzy goggles?
I think like I've really squinted, but I don't know. I think it's just wishful thinking. I think another interesting thing that one could potentially look at is like the geochemical signatures from the erupted products. So like in Iceland, there's a really clear, maybe you're aware of all this, but there's a very clear depletion in terms of like trace element geochemistry there. And so, you know, just from like the simple model that we've run, you would expect like a 40% depletion in some of these trace elements in West Antarctica, so that could be a signal to look for as well.
Great, thank you.
Yeah.
Thanks, Brent. Rob, perhaps you can ask your question by unmuting on Zoom, if you're still there. For Alex, thank you.
Sure, sorry, this is Alex. I was really stimulated by your talk, so I have another question that I started to think about at some point, and maybe you can inform me whether this is something that you and others are thinking about. If the whole ice shelf is flexing on tidal timescales, and therefore the grounding line is lifting on a, you know, lifting up and going down on some sort of tidal scale, and changing the opening to the subglacial system, that's not, obviously that's not a stagnant ocean. Is that something that you could think about in the context of the modeling you've done so far, or others working on that? And I'm particularly interested, as a water column person interested in particles, about the energy associated with that in resuspending sediments right at the grounding line and incorporating them into the buoyant meltwater seawater mix.
Yeah, thanks, Rob. So I referenced at the beginning of my talk these two papers by Ryan Walker and Roy Sayag from 2013, which are kind of the, I would say, the two main previous papers that have considered this issue of basically tidal pumping of water underneath ice sheets, and they come to somewhat different conclusions due to sort of different assumptions about what happens at the grounding line elastically. But the sort of nice thing, I guess, about sort of thinking about the two-layer problem is that you don't need tides. So previously it was thought that, or the sort of assumption going into those papers, and that in order to get any seawater upstream of the grounding line, basically in order for ocean water to be able to kind of move upstream against the hydropotential gradient in the subglacial hydrological system, you would need tides, basically as sort of overpressurization from the ocean. But that is only true under the assumption that there's no compositional differences between the two water masses. And so when you do have compositional differences, sort of as in this theory from Earl and then this generalization of Earl's theory, then you can vertically layer the two water layers. That's sort of what the intrusion is doing in this theory. And then the hydropotential gradient actually falls out of the theory. So it turns out not to be important. Now, of course, you can take the compositional differences and then you can add tides on top of that. And that sort of would be, potentially kind of one of the next steps is in order to think about what tidal currents do, what excess hydrostatic pressure does, these sorts of things. But at the very least, you don't need it in order to get some intrusion in this sort of situation.
Great. Thank you very much.
Come back if, sorry about that, I should have checked that. Okay. We'll come back to that one. Good question though. Okay, Nick Holshoe, you mentioned you have a question for Fiona. Would you like to unmute and ask that?
Thanks, Johnny, and thanks, Fiona. It was a great talk. I just had a quick question because I was thinking about partial melt as a problem, and fluids are great because they let you advect heat. So in the event that you have partial melt, you can transport all of that energy to the surface in the fluid. But I was thinking about what the latent heat implications are for melting a giant chunk of rock in the subsurface. And I realized I just didn't have a sense for the order of magnitude of the energy associated with that. Have you looked at how much heat is required to undergo the partial melt, and might that actually cool the country rock in that location and change the geothermal flux if, say, you're advecting all of that fluid away, the melted material? Then you're left with something that has to have given the heat away to provide for the melt. So yeah, I was just curious, have you looked at order of magnitude calculations for the latent heat consumed by that partial melting process, and if that affects the geotherm at all?
Sorry, the latent heat consumed by the melting of ice, or?
As you depressurize the rock and the rock has to undergo the phase transition, that has to take in latent heat and therefore cool the country rock. So I'm just wondering if that is a meaningful number or not.
Yeah, I think that, the primary contribution of, when I was doing these order of magnitude heat calculations, the primary contribution is the advection of warm mantle temperatures to the surface. I don't know if that really, so the assumption is that it's an adiabatic process as you're moving up to the surface. Maybe I'm not understanding the question.
Yeah, that's okay. I'd be curious to chat some other time about it. It's just, yeah, a very good talk. Thank you.
Okay. Yeah, I'm happy to talk offline too. Yeah. I'm curious to understand what your question is. Thank you.
Thanks for that. Yeah. So, Johann, are you still there? If you are, we could go back to the question from the room, and there's also a question for you in the chat.
Yes. I'm still here, and I just read the question, but something was wrong, I think, because I couldn't hear anything. Was it a live question? Probably.
Yeah. Sorry about if you couldn't hear it. So
okay.
It turns out the Zoom question is the same question.
Okay.
So maybe you could just address the Zoom question.
Yes, I think I get the question was about the grain shape data, which I showed in that one figure, but didn't say anything about because I couldn't put in everything that we did in those 8 minutes. But yeah, it was also very interesting with grain shapes because so we looked at quartz grains. And actually did first, of course, expect grains with cheddar marks, with striations or anything. So anything that would hint glacial transport or subglacial transport or any glacial origin. But in contrast, we actually found throughout the core nothing like it. We actually found very well rounded grains with high sphericities, and therefore that would rather point to fluvial transport, which then afterwards, because this is one of the first analyses we did, was corroborated by the biomarker data we got that actually point to this high inputs of organic matter. So the land probably was very near to the site. And then with these high, based on this high values in the bit index, we now know that most of this influx was facilitated by rivers and streams. So the fact that those grains are rounded to well-rounded sometimes really speaks now to very active fluvial activity on land that was most likely very nearby. I hope that answers the question.
Thank you. Fantastic. One more question from the room here.
Hey, Matthew, this question's for you. So thinking about sediment transport, I have seen these ridges since it was collected on the 1502 cruise, and I occasionally think about where did the sediment come from? These like isolated ridges, right, that don't seem to be connected. So I just wonder if you and your group have thought about that. And you know, like the morphology of those features is also interesting, sort of flat topped. So how did these things form? What do you think?
So we have thought about that in terms of their formation. And the current model is a near ice cliff morphology with either a very small ice shelf or no ice shelf at all. It'd be akin to something you'd see in Norway or Alaska, where you have these Daguerre moraines that are much smaller in volume, but tend to have a similar morphology, even though they're more pointed. We believe that the flat top has more to do with the morphology of the grounding line than anything else. And then their small volumes, being so separated as they are, has to do with the backstepping manner in which the ice stream collapsed backwards through time.
Thank you. I have one more question about what strikes me about these talks. So we're talking such vastly different timescales. And so I was going to ask you, Fiona, and perhaps connect up your work with Ricarda, measuring geothermal heat flow in some ways. Via how long would it take, how long does it take for present day ice sheet changes to change the thing that we measure geophysically, the Curie depth, or say just the geothermal heat flux? Is there a lag in the system, and what order of magnitude is that lag? I don't have a good intuition for it, so anything is useful.
Okay, so I don't really understand Curie depth temperatures. Maybe someone can explain that to me, but I mean, I think in terms of time scales, like we think of like melt processes happening, you know, at the fastest at like hundreds of meters per year, and at the slowest, you know, several orders of magnitude below that. And that's going to be, and then that's also going to be dependent on the manner in which melt is traveling through the lithosphere. If we're talking about, you know, this heat flux stuff specifically. And then I guess it's, so another question is also, there's been a lot of work that has looked at how deglaciation can influence like magmatic processes in the crust and lithosphere, like in terms of like triggering magma chambers and influencing dike propagation. I guess, yeah, and I guess I'm off on a tangent. Yeah, I was going somewhere with it.
No, I'll just follow. So, in a sense, the what Ricarda is mapping today is something to do with geothermal heat flux, and that if you're saying the timescale of evolution of response to ice sheet change is on the hundreds to many thousands of years, then the present day distribution is a function in part of past ice sheet topography. And I guess, is that something people have thought about, or you've thought about, and how to untangle those signals?
Yeah, I think, like I would expect these processes to be acting on the evolution of the ice sheet over like tens of kiloyears. That would be kind of the time scale that I have in mind. And then beyond that, I think, yeah, as you mentioned, it is like a very complicated process, and I don't think that there's an easy answer to, yeah, sorry.
Fantastic. I think that brings us to the end of the session. So thank you so much to all the speakers again, and it was on Zoom and in person. So round of applause, please. Thank you. And now we have a coffee break. A coffee break here, and a virtual coffee break for the NSF and NASA program managers. So stick around on Zoom for that.